You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. When we talk about how machines think, it is important to begin by recognizing that they do not think in the human sense. Instead of intuition, emotion, or creativity, machines rely on structured methods known as algorithms and data representations. An algorithm can be thought of as a recipe, a precise, step-by-step set of instructions for solving a problem or accomplishing a task. Just as a recipe tells you how to combine ingredients in a sequence to produce a meal, an algorithm tells a computer how to process input to reach an output. These instructions must be explicit, unambiguous, and complete, because computers cannot infer missing steps the way humans can. By following algorithms faithfully, machines simulate reasoning processes, performing tasks that appear intelligent, even though the thinking is mechanical in nature. For algorithms to work, machines need ways to represent data. Data representation is the process of encoding information, whether numbers, text, or images, into formats that computers can manipulate. For example, numbers are stored as binary sequences of ones and zeros, text is encoded through standards like ASCII or Unicode, and images are represented as grids of pixels with color values. To a machine, these representations are the raw material upon which algorithms operate. A facial recognition program, for instance, does not see a face as we do, but as a matrix of numbers corresponding to pixel intensities. Understanding how machines encode data reminds us that their thinking begins from abstractions of reality, which can be powerful but also limited in important ways. One of the earliest and most influential ways of representing knowledge in machines is through symbols. Symbolic representation involves modeling facts, concepts, and relationships as discrete symbols connected by logical rules. For example, a symbolic system might represent Socrates as a symbol, human as another, and mortal as a third, linking them with logical statements like, "All humans are mortal." This approach allows machines to perform deductive reasoning by manipulating these symbols according to established rules of logic. Symbolic AI dominated early research, reflecting the belief that intelligence could be captured by formal reasoning. While powerful in structured domains, symbolic systems often struggled with ambiguity, uncertainty, and real-world messiness. Still, they provide a useful illustration of how machines can simulate aspects of human reasoning by treating knowledge as a network of symbols. Search algorithms represent another fundamental way in which machines think. These methods allow computers to navigate problem spaces by systematically exploring possibilities. Depth-first search, for example, pursues one branch of options deeply before backtracking, while breadth-first search examines all possibilities at each level before moving deeper. Such approaches are useful in puzzles, pathfinding, and decision-making tasks. A chess program, for instance, can search possible moves several steps ahead, weighing outcomes to select a promising strategy. Search algorithms demonstrate the mechanical rigor of machine problem-solving. They are exhaustive, methodical, and often faster than human reasoning in structured settings. Yet they also illustrate the challenge of complexity. Without shortcuts, the sheer number of possibilities can overwhelm even the fastest computers. To address this problem of overwhelming possibilities, heuristics play a key role. A heuristic is a rule of thumb or shortcut that guides search toward promising solutions without guaranteeing perfection. Humans use heuristics all the time, choosing the road that looks shorter when driving or starting with the most common causes when diagnosing a problem. In AI, heuristics allow search algorithms to prune unlikely paths and focus on areas more likely to yield results. For example, in chess, a heuristic might prioritize moves that protect valuable pieces. While heuristics improve efficiency, they can also introduce biases or lead to suboptimal outcomes. They highlight the trade-off between exhaustive precision and practical problem-solving, showing how machines, like humans, often balance thoroughness with efficiency. Graph representations provide another powerful way for machines to structure knowledge. A graph consists of nodes which represent entities, and edges which represent relationships between them. This structure is particularly effective for modeling networks, such as transportation systems, social connections, or communication pathways. For instance, Google's search algorithm originally relied heavily on graph representations of web pages and their links, treating each page as a node and each hyperlink as an edge. Graphs enable machines to solve problems such as finding the shortest route between two cities or identifying influential individuals in a social network. By representing relationships explicitly, graphs allow algorithms to reason not just about individual data points but about the connections that give them context and meaning. Another way machines approach problems is through state space representation. In this framework, a problem is defined as a collection of states, along with rules for transitioning between them. Each state represents a snapshot of the problem at a given moment, while transitions describe the actions that move from one state to another. For example, in a puzzle like the Rubik's Cube, each arrangement of the cube is a state, and each twist of a face is a transition. The goal is defined as reaching a particular state, such as a solved cube. This approach allows algorithms to frame problems systematically, searching paths through the state space to reach desired outcomes. State spaces illustrate how machines map out possibilities in structured, logical ways. Rule-based reasoning is another cornerstone of early AI approaches. In this method, knowledge is encoded as collections of if-then rules. For example, if the patient has a fever and cough, then consider flu. Expert systems in medicine and business often relied on thousands of such rules, capturing the expertise of human professionals. These systems could perform surprisingly well in narrow domains, applying consistent logic to large sets of conditions. However, they also struggled when faced with incomplete or contradictory information, as real-world scenarios rarely fit neatly into rigid rules. Rule-based reasoning shows both the promise and the limitations of encoding expertise explicitly. It is transparent and explainable but brittle and labor-intensive to maintain. Probabilistic models introduced a way for machines to handle uncertainty. Instead of insisting on absolute rules, these models assign probabilities to outcomes, reflecting the likelihood of different possibilities. For example, a spam filter may calculate that an email has a 90% probability of being spam based on its content and sender. Probabilistic approaches, such as Bayesian inference, allow machines to make informed guesses in the face of incomplete or noisy data. This mirrors real-world reasoning, where humans rarely deal in absolutes but weigh evidence to make decisions. By incorporating probability, AI systems became more flexible and realistic, better suited to messy environments where certainty is rare. Optimization algorithms represent another way machines think, focusing on finding the best solution among many alternatives. Optimization problems appear across countless domains, minimizing fuel use in logistics, maximizing profit in business, or training a machine learning model to reduce error. Algorithms like gradient descent, for instance, adjust parameters step by step to minimize loss functions in neural networks. Optimization is essentially about balancing competing factors to reach the most desirable outcome. These methods underscore the mathematical rigor underlying machine reasoning. While humans might rely on intuition to eyeball the best choice, machines systematically search for optima according to well-defined criteria. Pattern recognition illustrates yet another dimension of machine thinking. Algorithms trained on datasets can detect recurring structures, whether in images, sounds, or sequences. A face recognition system, for example, learns to identify patterns of features like eyes, nose, and mouth. Speech recognition systems detect patterns in sound waves that correspond to phonemes and words. Pattern recognition is powerful because much of human intelligence also relies on spotting regularities in experience. For machines, this ability to generalize from patterns forms the foundation of many practical applications, from fraud detection to medical diagnostics. It shows how algorithms can approximate human perception by systematically analyzing data for meaningful regularities. Feature engineering plays a central role in traditional machine learning, where raw data is transformed into meaningful attributes that models can use effectively. For instance, in a credit scoring model, raw data like transaction histories might be converted into features such as average monthly spending or payment regularity. Well-designed features make it easier for algorithms to detect useful patterns, while poor features hinder performance. Feature engineering is often a creative and domain-specific task, requiring human expertise to decide what aspects of data matter most. This process highlights the collaborative nature of machine thinking. While algorithms process data, humans shape the representations that make learning possible. Neural representations introduced a new paradigm, where information is stored not as explicit rules or features, but as distributed patterns of weights and connections among artificial neurons. In this framework, knowledge is encoded implicitly across many parameters, allowing networks to capture subtle, nonlinear relationships. For example, a deep neural network trained on images may not store a single rule for what makes a cat, but instead encodes catness as a web of interconnected patterns across millions of weights. Neural representations are less interpretable, but more powerful in handling complexity. They represent a departure from symbolic reasoning, favoring emergent patterns over explicit logic as the core of machine intelligence. Abstraction is key to making machine reasoning scalable. By building layers of representation, machines can process increasingly complex tasks. Just as humans abstract from letters to words to ideas, machines move from raw pixels to shapes to objects, or from sound waves to phonemes to sentences. Abstraction allows algorithms to manage complexity by grouping details into higher-level concepts. For learners, this idea explains why layered architectures like deep learning networks are so effective. They mimic the human ability to build understanding step by step. Abstraction is not just a technical strategy, but a conceptual bridge between simple data and complex reasoning. Despite these impressive methods, machines remain limited in their thinking. Algorithms lack human qualities such as intuition, creativity, and genuine understanding. A machine may outperform a doctor in recognizing tumors in scans, but cannot comfort a patient or understand the broader context of care. Algorithms can simulate aspects of reasoning, but they do not know in the way humans do. These limitations remind us that AI, however advanced, is a tool powerful, precise, and sometimes uncanny, but not a replacement for human judgment. Recognizing these boundaries helps learners maintain a balanced view. Machines think in structured, algorithmic ways, while human intelligence remains broader, richer, and deeply contextual. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. One of the most fundamental distinctions in machine reasoning lies between deterministic and probabilistic approaches. Deterministic algorithms guarantee the same output every time, given the same input. A sorting algorithm that organizes numbers from smallest to largest will always produce the same result for a given list. Probabilistic approaches, by contrast, deal with uncertainty and produce outputs that incorporate degrees of likelihood. A spam filter, for example, may classify an email as 85% likely spam. These two approaches reflect different philosophies of reasoning. Determinism offers certainty and reproducibility, while probability provides flexibility and uncertain conditions. In practice, both are vital. Deterministic algorithms underpin reliable computing, while probabilistic methods allow machines to navigate messy, real-world data where absolutes are rare. This duality illustrates how machine thinking balances rigid precision with adaptive inference. The contrast between symbolic AI and sub-symbolic AI offers another lens for understanding machine reasoning. Symbolic AI, rooted in logic and explicit rules, represents knowledge as discrete symbols manipulated by formal processes. Sub-symbolic AI, by contrast, relies on pattern recognition in distributed systems like neural networks, where knowledge emerges from the interplay of many small units. Symbolic AI excels in transparency and structured problem-solving but falters in handling noise and ambiguity. Sub-symbolic AI thrives in perception tasks like vision or speech but is harder to interpret. These approaches are often viewed as complementary rather than competitive. For learners, the distinction highlights the diversity of strategies machines use to approximate intelligence, showing that thinking can emerge either from precise rules or from emergent patterns. Representation in machine learning models is a crucial concept. Unlike symbolic systems that explicitly store facts and rules, ML models encode patterns gleaned from training data. For example, a linear regression model represents knowledge as coefficients linking input variables to outcomes. A decision tree represents knowledge as branches of conditions leading to predictions. Deep neural networks go further, embedding knowledge in millions of interconnected weights. These representations allow machines to generalize from examples, capturing relationships not explicitly programmed. Understanding representation is essential because it defines what a model knows and how it applies that knowledge. Learners should appreciate that in AI, representation is not just about storage. It shapes reasoning, influencing accuracy, bias, and interpretability. Vector representations provide a powerful way to make data machine readable. In this approach, words, images, or sounds are transformed into numeric arrays or vectors that capture their properties in multidimensional space. For instance, the word king might be represented as a vector in a way that its relationship to queen is analogous to the relationship between man and woman. Images can be represented as vectors of pixel intensities and sounds as vectors of frequency components. This mathematical encoding enables algorithms to compute similarities, differences, and transformations efficiently. Vector representations illustrate how machines reframe qualitative phenomena into quantitative forms, making them accessible to algorithms that operate on numbers rather than meanings. Embeddings in natural language processing extend vector representations by capturing semantic meaning in dense vector spaces. Instead of assigning arbitrary numbers to words, embeddings position words in such a way that similar meanings are located close together. For example, dog and puppy would appear near each other, while car would be farther away. These embeddings are learned from vast text corpora, allowing machines to model linguistic relationships beyond simple dictionary definitions. Embeddings power applications such as translation, sentiment analysis, and conversational agents. For learners, embeddings demonstrate how abstract concepts like meaning can be approximated through mathematical geometry, enabling machines to navigate the richness of language without explicit rules for every word or phrase. Latent features in deep learning highlight how machines can discover abstract patterns automatically. Hidden layers within a neural network extract features not directly visible in the raw data. For instance, in image recognition, early layers may detect edges, middle layers identify textures, and deeper layers recognize objects like cats or cars. These latent features are not pre-programmed but emerge from training, reflecting the network's internal organization of knowledge. This capacity to discover features autonomously distinguishes deep learning from traditional methods that rely heavily on human-designed attributes. Latent features illustrate both the power and the opacity of deep models. They enable extraordinary performance, but often resist straightforward interpretation. Model generalization is the ability of an algorithm to apply what it has learned from training data to new, unseen examples. A well-generalized model recognizes underlying patterns rather than memorizing specific details. For example, a model trained to recognize handwriting should identify a new person's writing style, even if it was not in the training set. Generalization is the ultimate test of machine learning, because without it, models remain narrow and brittle. Achieving good generalization requires balanced training, sufficient data diversity, and careful design. For learners, understanding generalization clarifies why large, varied datasets and thoughtful evaluation are so critical in building trustworthy AI systems. Two common pitfalls in machine learning are overfitting and underfitting. Overfitting occurs when a model learns the training data too well, capturing noise and idiosyncrasies that do not generalize to new cases. Underfitting, by contrast, happens when the model fails to capture important patterns, remaining too simplistic. A good analogy is studying for an exam. Overfitting is like memorizing specific practice questions without understanding concepts, while underfitting is like skimming so lightly that you never grasp the material. Both lead to poor performance on new challenges. Striking the right balance is the art of model design, requiring tuning, validation, and sometimes trade-offs between complexity and simplicity. Representation plays a critical role in computer vision. Raw images are composed of pixels, which machines process as arrays of color values. Algorithms transform these pixels into higher-level features, edges, shapes, textures, and eventually objects. Deep convolutional networks automate this process, building hierarchical representations that allow recognition of complex scenes. For example, distinguishing a cat in a photo requires moving from low-level pixel patterns to the high-level concept of cat. This layered representation explains how machines approximate visual perception. It also highlights limitations. A system may misinterpret unusual lighting or distorted images, revealing the fragile link between numeric representations and real-world objects. Speech recognition presents another example of representation in action. Sound waves are continuous signals, which machines convert into discrete features such as frequency spectra or phonemes. These representations capture the building blocks of language, allowing algorithms to map them to words and sentences. Advances in deep learning have improved this process, enabling systems to handle accents, noise, and variations in speech more effectively. However, the process remains imperfect, as meaning depends heavily on context and intonation. For learners, speech recognition illustrates the challenge of transforming raw sensory data into structured representations, showing how algorithms approximate but do not replicate human understanding. The symbol grounding problem raises a deeper philosophical issue. How do machine representations connect to real-world meaning? A computer can manipulate symbols like dog or vectors representing an image, but does it truly understand what a dog is? Without grounding in experience, symbols risk being abstract tokens without context. This challenge remains unresolved, highlighting the difference between human and machine cognition. While machines can approximate meaning through correlations and embeddings, their understanding is fundamentally statistical rather than experiential. The grounding problem reminds us of the limits of algorithmic reasoning and the complexity of bridging representation to genuine comprehension. Transparency of representations is a growing concern in AI. Some models, like decision trees, are relatively interpretable, showing how inputs lead to outputs. Deep neural networks, by contrast, often function as opaque black boxes. Lack of transparency raises issues of trust, accountability, and fairness, particularly in sensitive domains such as healthcare, finance, or law. Researchers are developing tools for explainable AI, aiming to make internal representations more interpretable. For learners, transparency underscores why representation is not only a technical matter, but also a societal one. Clear representations build confidence and enable oversight, while opaque ones risk undermining trust in AI systems. Trade-offs are inherent in algorithm design. Designers must balance speed, accuracy, interpretability, and resource use. A fast algorithm may sacrifice accuracy, while a highly accurate deep model may demand enormous computing power. Similarly, a transparent model may be less powerful, while a complex model may be more effective but inscrutable. These trade-offs mirror real-world decision-making, where perfect solutions are rare and compromises are necessary. Understanding these dynamics helps learners appreciate that algorithms are not chosen in a vacuum. They are shaped by context, goals, and constraints. Recognizing trade-offs prepares learners to think critically about which methods suit particular problems. Hybrid representation models are gaining attention as researchers seek to combine the strengths of symbolic and neural approaches. By blending explicit logic with data-driven learning, hybrid systems aim to achieve both interpretability and adaptability. For example, a hybrid legal reasoning system might use rules to capture statutes while relying on deep learning to interpret complex text. These models promise greater robustness, bridging the gap between structured reasoning and flexible pattern recognition. They also illustrate a broader trend in AI, convergence of methods rather than dominance of a single paradigm. For learners, hybrid approaches highlight the importance of integration, showing that AI's future may rest in combining rather than isolating different techniques. Ultimately, understanding algorithms and representations prepares learners for more advanced topics in machine learning and deep learning. These concepts provide the foundation upon which modern AI is built, clarifying how machines process, structure, and manipulate information to approximate intelligence. By grasping these fundamentals, learners can better navigate the complexities of later episodes, appreciating both the power and the limitations of machine reasoning. Algorithms and representations are not merely technical details, they are the very language in which machines think, shaping every application and every breakthrough in artificial intelligence. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.